Hi everyone, this is the compressed sensing group, and let's jump right into it. So why compressed sensing? So compressed sensing helps to boost the speed of K-space acquisition, and we can do this by performing a random undersampling of K-space. And so this results in an undetermined system with a multitude of different reconstruction methods that we'll go ahead and cover today. And so how exactly do you go about compressed sensing? So the way you would go about compressed sensing is that you have a random mask that's applied to K-space, multiplied by some set of Fourier coefficients to get back our reconstruction image. And so we want to minimize the S vector or the sparsity vector such that the observation of our image, which is the randomly sampled K-space times the sparsity vector, subtracted from our idealized image, we want that difference essentially to be negligible. And so for this to work, for comparison sensing to work in general, we need our measurement to be sparse enough and our mask must be incoherent and non-parallel. And so we've created an app to handle random mask generation and to also apply different reconstruction methods to our image, just to simulate all this. So as you can see, we can play around with the concentration of how many points are centered in the center of where we centered it according to the Y and X axis. The full width half maximum, we can control like the width of the entire function as it spans across the space. As well as the density, or how much ones basically appear within our random mask. And so, as I've already mentioned, we use a point spread function to essentially concentrate points in the middle. And so, just a little bit more of a deep dive, we have essentially a low-pass filter based on a certain density threshold that we provide to allow certain mask values to go through or not pass through.
Once we've collected that data in the K-space, we can apply it to a wavelet or a DCT sparsity function. Shown here, we have the wavelet function with and a threshold applied on the left. So the threshold essentially says anything below that threshold value is what we're going to consider noise. And we can see how we're doing that again in the DCT. And this effectively is, depending on what we set as a threshold, we can say what is the values that are important to us. And this is what makes it sparse, because rather than taking all these data points, now only the ones that are peaking out over some level that we consider important, those are the ones that we are conserving. So we're not taking all these little information here. So the DCT goes right into the conjugate gradient in our code. As you can see here at the bottom of the code, we applied that threshold and we multiply it by some lambda value, which is the weighting that says how much of this data that we're putting back in, how important we want it to be, right? This is consistent with the general formula for a conjugate gradient, wherein you're trying to minimize the sum of both the data consistency and the image. And what we can see here, obviously from this gradient, we can see that it's a purely additive method. We're only adding things back in, right? So the idea is to boost your signal. However, we can see that it was not really good, but is still clearly doing something because our data consistency is reducing and so is the gradient, right? So here, as we look closer, we can see it's really visually difficult to see because was performed with purely just the algorithm and not using the compress or not using the controlled undersampling. So a lot of this incoherent noise we can take out once we do the proper procedure, use the proper sampling. And we can see what this conjugate gradient actually does is it adds the information back in to make the image brighter. However, it's also adding information on some of the noise, meaning it really struggles to reduce the actual noise. And speaking of noise problems, if you have a large lambda, for example, remember the lambda is added onto the sparsity. That means you're increasing how much of that sparse space you're adding back on, which of course means you're amplifying the noise a bit more, and it gives you this very grainy image. The same thing is same effect happens if you don't threshold your sparse vector. It becomes completely incoherent. And maybe you can see some stuff, but it's not useful. So here, this is just a code to show the actual iterative step as you go through every time. It's modulating your alpha, it's modulating the search direction with the beta, and it's adding the alpha and the p-value, which is the gradient, the new gradient. It adds it back in to update the solution, and it does this repeatedly. Over time, it should shrink such that it's adding less and less on, and you're getting closer and closer to converging at your image. But how do we actually remove some of that noise? As you can see, that's not really helpful if we have so much noise. Well, we can use the alternating direction method multiplier, or ADMM. It just essentially separates the Lagrangian of the x and the z so that we can solve for them separately. And then it updates the Lagrange multipliers using a gradient ascent. We can see this method done here. U is essentially a variable that stores the noise from that is the non-sparse noise, right? So if we look at how we calculate that, the U is the previous U plus whatever the new difference between your sparse and your image and your sparse image. That difference should be the noise. So when you're adding it back in, you're adding some of the information back in, but then, or rather when you're subtracting it because there's a negative sign here, you're subtracting your noise and then you're adding it back in again. However, without the 1 minus mask, you're adding it over the whole region. So you're adding some of the important information back on. And here's just the regularization parameter that we have for our wavelet thresholding. And now we can see that it actually seems to be reducing the noise a little bit. It's smoothing it out. However, it also smooths out the image. But that's okay. Once we apply our undersampling method and control where we sample in K-space, we can actually reduce all that incoherent noise and preserve some of or brighten up some of the key geometry features of this brain image. And as we can see, our data consistency is still going down, meaning it is getting closer to an ideal image.
So now let me introduce you guys a different algorithm, which is called fast iterative shrinkage threshold algorithm. Well, let me just briefly explain what ISTA is beforehand. So it basically contains two parts. The first part is the data fidelity term, and it's matching the reconstruction with the data we observe. And the second part is the sparsity regularization term, which is introduced sparsity. So the base logic behind this algorithm include two parts. The first part is a gradient step. The second part is a threshold step. So basically, it update gradient and compute accelerated intermediate point. And it also applies a soft threshold operation, so it tuned with the threshold for each iterations. Next slide, please. So what is the fast, which is the FISTA here? So it basically, instead of using a constant speed of each iterations, it introduced a momentum parameter TK to adjust accelerations. So for each iteration, the speed to run the iteration now is actually built upon the conditions of a previous iteration result. So this accelerates and it provides a faster convergence. Next slide, please. So as you can see on the right-hand side is our original image. On the right-hand side is our the undersampled K-space. Size. And so on the left-hand side is a direct image from backwards reconstructed from FFT. And on the right-hand side is a reconstructed image using the FISTA. So here you can see that it's actually deblurring it quite well, where you can see the geometry shape quite well of each organism, but it really didn't do that much on the denoising part, which means that the noise is still a big issue under this algorithm. Next slide, please. So we want to get rid of the noise to see, is it really the noise issue or is it just this algorithm is something off? So we create a image with just blur without any noise, and we see that it's actually deblurring quite well. Just there's lots of artifacts there. Next slide, please. And this is just showing you guys the MATLAB code where you can see the relative differences between each iteratives on the right-hand side. Next slide, please. And on the left-hand side, instead of using a back calculation, the algorithm of equals to periodic, I use a zero of back construction, and you see it's really altered with the reconstruction image. And it's on the right-hand side is where I use a really low iteration number, which equals 20, and you can see the resolution is really off. Next slide, please. And we also want to test what if we can use the FISTA upon the ADMM. So upon different reconstruction algorithms. So we have the ADM reconstructed image on the left-hand side. I denoise it. It seems like it's affecting it a little bit, but it's not that much. And after that, I apply deep blur on it. It's doing quite well, but you can still see the huge noise in the center of the image.
So in conclusion, randomness is too important to be left to chance. Controlling the undersampling is critical to removing a large degree of incoherent noise. So seen in the app, controlling the X and Y parameters or controlling the density, concentration, or full with half maximum is just critical to be able to find the frequencies in the center and reconstruct your image.
Additionally, the thresholding and the regularization parameters are really important because those determine how you weight your sparsity, and really decides, between the data consistency and the sparsity. That is how you're trying to find a balance between those. It's highly sensitive, which is why in our future directions, we'd like to see how it interacts with, or how it affects when you're looking at different tissue types, whereas different levels of contrast between something hard like bone versus other tissues or fat and muscle, things like that, because presumably it's not going to be a one size fit all, regardless whether you're doing ADMM or conjugate gradient descent.
And so for FISTA, it's really a trade-off between the ability of deblurring and denoise and the speed. So we can run around 3,000 iterations within just 3 minutes, but the deblurring and denoise is really not as that good as with the ADMM algorithm. So we want to tune the parameter to see if we can shoot the limits of the ability of this algorithm, and we want to explore more combinations of reconstruction algorithms we build upon.
All right, thank you so much. This has been our presentation on compressed sensing, and there we go.